So this is the 49th session on relative velocity. So in this video also we'll discuss more problems on relative velocity for mutually translating frames. Okay. I will write down the assumptions in this problem. What data are given, what is not given, what we have to find, etc. It is something like this. This is the frame F. This is the frame M. M translating with respect to F. Velocity of M with respect to F is VMF. P is the moving point under observation. So VPF equal to, from the formula of translating frame, VPF equal to VPM plus VMF. Alright. Now in 49th session, it will assume that VMF is known fully in magnitude and direction both. VPM only magnitude is known, not its direction. Magnitude is that is known, and magnitude is given, but its direction is unknown. And VPF direction is known, but magnitude is unknown. Direction is known, but magnitude is unknown. Okay. So in this problem, mainly we have to find the magnitude of VPF. Okay. If we find VPF, then this problem will be solved. All right. Now, while going ahead, one thing has to be noted. Suppose C is the resultant of two vectors A and B. All right. So C. Suppose this is the vector A. This is the vector B. We complete the parallelogram with A and B as adjacent sides. Diagonal of this parallelogram through the common tail of A and B, that is vector C. Suppose this angle is alpha, this angle is beta. This is the vector C. Suppose unit vector along C is n1 hat and unit vector normal to C is along n2 hat. Okay. So C is equal to A plus B. Alright. Now what we do, we take the component of this equation along with n1. We dot this equation with n1. So C dot n1 hat, A dot n1 hat plus B dot n1 hat. Now C dot n1 hat becomes C into 1 into cos 0, that is just C. And A dot n1 hat becomes what? A in this way, n1 in this way. A dot n1 hat becomes A into 1 into cos of alpha. And what about B dot n1 hat? B makes an angle of, this is right angle. So B makes an angle of 90 plus alpha with vector. B makes an angle of beta with vector B dot n1 hat. N1 hat is in this way, sorry. C dot n1 hat is C. A dot n1 hat is A into 1 into cos alpha. And B dot n1 hat, B is this, n1 is this. Angle is beta. So this becomes B into 1 into cos of beta. So C becomes A cos alpha plus B cos beta. This one result, okay. But one more thing, n2 is a unit vector normal to n1 hat, that is normal to vector C. So from this we see that C dot n2 hat is 0 because they are mutually perpendicular, and dot product of two mutually perpendicular vectors is 0. So C dot n2 hat becomes what? 0. Now instead of C we write A plus B. So we write here vector A plus vector B dot n2 hat is 0. So this means A dot n2 hat plus B dot n2 hat is 0. Now what about A dot n2 hat? This becomes A into 1 into cos of angle between A and n2 hat. A is in this way, n2 is this way. This angle becomes 90 plus alpha. So cos of 90 degree plus alpha plus B dot n2. Now B dot n2 is what? B into into 1 into cos pi by 2 minus beta. B into 1 into cos of pi by 2 minus beta, that is 0. So this becomes minus A sin alpha plus B sin beta is 0. So this means A sin alpha is equal to B sin beta. So these two results have to be kept in mind because they will be useful in solving the problems of case 3, case which we are going to discuss in this video. So A sin alpha is equal to B sin beta. Okay, fine. So these two results have to be kept in mind. Okay, fine. So C is equal to A cos alpha plus B cos beta, and A sin alpha is equal to B sin beta. Alright. Now I'll wrap this, okay? This also I wrap it, okay? Now see, I'll write down that vector equation again. VPF equal to VPM plus VMF. As I stated, this is the problem of case 3. Okay. And case 3, 46 video I have given the details. This is the problem of case 3. VMF complete information is known. VPM only magnitude known. Direction unknown. और इसका only direction known. Only direction is known. All right. VPM, so VMF is known in both magnitude and direction. So VPM only magnitude is known, and for VPF only direction is known. So main the problems revolves around finding the magnitude of VPF. Okay. Finding the magnitude of what? VPF. All we have to find is to determine the magnitude of vector VPF. Magnitude of vector VPF has to be determined. Okay. Then problem will be solved. So now for this we have to draw the diagram. Okay. Now we have to draw the diagram as per the parallelogram law of vector addition. Okay. Suppose for the time being, assume that these two vectors are known. Then how do we draw VPF? We draw the arrow for VMF. We draw the arrow for VPM. Then we, with these adjacent sides, we complete the parallelogram. We draw the diagonal of this parallelogram, so the common tail of these two vectors. This is the vector VPF. So VPF is drawn in this way, assuming these two are known. Alright. I got this, okay? Now, but here, this method is to be followed when these two vectors are known in magnitude and direction both. But in this problem, only this is known, and for this only magnitude is known, direction is not known. And VPF, we know the magnitude, direction, okay, and for this we know the magnitude. So what? How do you draw this diagram in this case? See, we know the direction of VMF and VPF, okay. So what do? We draw the arrow for VMF, okay. Okay, say this one. We also know the direction of VPF. So see, in this diagram, these three vectors have a common tail. Okay. So if we know these two and we draw this one. Now, but actually this is not known direction wise. So what we draw these two vectors so that the tails coincide. So I draw this vector VPF. Okay. So the tails of these two vectors coincide. Now this is the diagonal of this parallelogram. The diagonal of parallelogram lies inside the triangle, inside the parallelogram, not outside it. So VPM should be on the side of VPF, not containing VMF. See, this is the VPF. This is the VMF which lies on this side of VPF. So VPM should be on the side of VPF, not containing VMF. So VPM should be something like this. If this is VPMF, this is VPM, this is VPF. VPM lies on the side of VPF, not containing VMF. VMF is on this side of VPF. So VPM should be on this side of VPF. VPM should be on this side of VPF. So this should be VPM. And then what we do? We complete this parallelogram. Okay. So here we get two triangles, two congruent triangles. Now in these two subcases arise. One, both the triangles are right angle. Both the triangles are right angled. In that case, we can find VPF direct by Pythagoras theorem. So there is no problem at all. But second, if this triangle is not right angle, either of these two triangles are not right angle. If these two triangles are not right angled, in that case, suppose we assume that this angle is alpha, this beta. Then what we do? We write the VPF as I just wrote for vector A, B, C, alpha, beta. I write VPF as VPM cos beta plus VMF into cos alpha. This becomes VPF. And one more thing, one more equation I wrote, A and B, C, that applied here. So that becomes VPM sin beta is equal to VMF sin alpha. Now this is known, VPM is known, from this beta can be determined. We substitute beta in this equation. This is known, this is known, this is known, this is known, then VPF can be determined. Once VPF is determined, the problem can be solved. Fine, alright. Is it clear? Fine. So if it is right angle triangle, we directly deal with any other triangle and apply the Pythagoras theorem. So this square equals this square plus this square, from that VPF can be determined. Okay. And second is these two triangles are not right angle, then we apply that concept here. From this, alpha is known, VMF is known, VPM is known, beta can be determined. Beta can be determined, beta is substituted in this equation. VPM is known, beta is known, VMF is known, alpha is known, so VPF can be determined. When VPF has been determined, problem is fully solved. Fine, alright. Now I'll rub this, okay? So I'll take a problem to illustrate this concept, alright? So I'll write down the problem. Problem is this. Problem is this. C1 and C2 are two cities. C1 and C2 are two cities which are separated by a distance L, and C2 is due east of C1. C2 is due east of what? C1. Air flows at a constant speed u with respect to ground towards north. An aeroplane flies from C1 to C2 and then back to C1, and speed of plane with respect to air, that is still air, is v. See, when we say velocity of plane with respect to air is v, we can state it another way as velocity of a plane in still air, that is v. It's just a way of saying it, okay? I'll wrap this, okay? Also, v is more than u, okay? So question is, find the time taken by the plane for the complete journey. The time taken by the plane for the complete journey. Time taken by plane for the complete journey. Okay, this is the question. So first of all, what we do, we identify the object. Object under consideration is aeroplane. Aeroplane is the object under consideration, denoted by P, say. Instead of M frame, we have air, which is denoted by A, say. Instead of F frame, we have ground, denoted by G, say. Okay. Now what do? We write down the vector equation for translating frames. VPG is equal to VPA plus VAG. Alright. Now see, VAG is fully known. It has a magnitude of U. towards north. Full information of VAG is given. For VPA, we only know the magnitude V, but its direction is not known. That is the heading of plane in this case. VPA gives the heading of the plane. Direction of VPA is the heading of the plane. As in case of reverse man problem, VSR gives the heading of swimmer. So VPA gives the heading of the plane. And VPG is the velocity of plane with respect to ground. So magnitude is also not known. But while going from C1 to C2 and back to C1, direction of VPG is known. So this problem is of case 3. It is a problem of case 3. Alright. It's a problem of what? Case 3. This is the case 3 problem. Okay. So now how do we start the problem? That is the question. Find the time taken by the plane for the complete journey. Suppose the time taken by the plane for the complete journey is t. That is equal to sum of time t1 plus t2. Where t1 is the time taken by the plane to move from c1 to c2. And t2 is the time taken by the plane to fly from c2 to c1. Alright. I got this, okay? So to know t, we have to know t1 and t2. First we find t1. t1 is the time taken by the plane to fly from c1 to c2. Now plane flies from c1 to c2 with respect to ground. So distance covered by plane with respect to ground is L, and speed of plane with respect to ground is constant. So time taken is equal to distance by speed. Distance moved by plane with respect to ground, that is L, is divided by speed of plane with respect to ground, Vpg1. Now to know t1 we must know L and Vpg1. But L is already known. We only have to find Vpg1. For that we write down the vector equation for the first half of the journey. So we write Vpg1 is equal to velocity of plane with respect to air, Vpa, plus velocity of air with respect to ground. Alright. Now we know VAG full information, U towards north, full information is given. Vpg1 we know the direction from C1 to C2 towards east. And for Vpa we know the magnitude V, but we don't know the direction of Vpa. Therefore it is a problem of case 3. Now how to find the value of t1? For that we must first draw the vector diagram. Now we are given the vector VAG, magnitude, direction both. We know the magnitude of this vector and we know the direction of Vpg1. So what we do, as I discussed just now for the theory of this video, in beginning of this video, I will draw the arrows for these two vectors, this and this. This is known VAG. VAG is towards north. This VAG, it is U. Now we draw the arrow for Vpg1 with its tail coinciding with this one. The Vpg1 is in this direction. Okay. This Vpg1 is just equal to what? Vpg1. Fine. Now we have to draw the vector Vpa. Vpa has the magnitude of V. Now this is the diagonal of the parallelogram. So Vpa should be on the side of Vpg1 not containing VAG. That is, Vpa should be something on this side. So this should be equal to Vpa. That is Vpac. Vpa. This is just equal to V. Okay. Then what I do? With these adjacent side, we complete the parallelogram. Okay. Fine. So see, I get two right angle triangles. They are congruent triangles. So from directly we can say this is U. This is V. So this is also V. Parallelogram law of vector addition. And this is what? Vpg1. So this square plus this square equal to this square. Pythagoras theorem. So V square equal to U square plus Vpg1 square. So this means Vpg1 is simply equal to V square minus U square. Fine. Alright. Now I love this, okay? So this is we have obtained. We substitute here. We get T1. So T1 is equal to root under L by root under V square minus U square. So we have obtained T1. Now we have to determine the value of T2. T2 has to be determined. Now T2 is the time taken by the plane to fly from C2 to C1. So again, with respect to ground, the plane covers a distance of L at a constant speed of say Vpg2. The time taken is distance by speed. Now to find T2, we must know Vpg2. For that again, we write down the vector equation. So Vpg2 is something like this. Velocity of plane in respect to air, Vpa2, plus velocity of air in respect to ground, that is Vag. Now Vag, we know the complete information, u towards north, full information is known. For this we only know the magnitude, v is known, direction is unknown. For this we know the direction from C2 to C1 towards west, so we know the direction. Again it's problem of case 3. Okay, again to find this Vpg2 we draw the vector diagram. Now we are given the vectors Vag, full information, and for this we know magnitude, we know the direction. So what we draw these two vectors with the tails coinciding. So Vag is this side u, and Vpg2 is in this direction. This is just Vpg2. Okay, so now Vpa2 is on side of Vpg2 not containing Vag, that is on this side. It is approximately this one. This is Vpa2, that is just V. Now with these two as the adjacent side, we complete the parallelogram. Again we get two right angle triangles, we can directly deal with it. So this is u, this is v, this is also v, parallelogram, opposite sides of parallelogram. This is Vpg2, this square plus this square equal to this square, Pythagoras theorem. V square equal to u square plus Vpg2 square. So Vpg2 becomes root under v square minus what? U square. This becomes Vpg2. Fine. I substitute here. So T2 is also obtained. L by root under v square minus u square. Fine. So I have this. Okay. So T2 is also obtained, T1 is also obtained. So T is just equal to T1 plus T2, that is equal to 2L by root under V square minus U square is therefore the required answer. See, for this to be defined, it is necessary that V should be more than U. Otherwise, if V is less than U, then this root becomes undefined. So in that plane will not be able to complete the journey. Okay, not be able to fly from C1 to C2. Fine. So this is the answer of this. Okay. So in 49th session, I have taken the problem on case 3. I have discussed the theory of case 3. I have discussed fully. I have taken a problem on case 3 in session 49. Okay. In the next session also, I will take up some in next few sessions, coming 3 to 4 sessions. I will be taking up problems on this third case. Alright. I will be taking up problems on this which case? Third case. Alright. So I will close it here. Fine.